Good afternoon and welcome to my video, where today we'll be talking about an adiabatic flame temperature. More specifically, we'll be explaining how the moles of each species in the feed and product are determined from the reaction stoichiometry and given the excess of air. More specifically, we'll be using this situation where the natural gas comprising 95 mole percentage of methane, 4 mole percentage of ethane, and 1 mole percentage of propane burns with 20% of excess air. We'll be using this information to calculate the adiabatic flame temperature in our code in Python. So let's go ahead and get started. First things first, we see that this is an adiabatic flame temperature where we have some sort of flame, some sort of fire, say it's Bunsen burner or some sort of fire, and we have two things going in, right? We have the fuel going in, which is our methane, ethane, and propane, right? As well as we have air, right? We have the air that is helping this reaction take place. And this air, more specifically, it is proportional as it is 21 mole percentage of oxygen compared to 79 moles percentage of nitrogen gas, right? You have it. Okay, but let's get started. So we know that we have natural gas with these three things: methane, ethane, and propane. We know what methane is. We know that it is one carbon connected to 4 different hydrogens. So we have CH4 for methane. And ethane is with an extra carbon. We have 2 carbons, C2, and a total of 6 hydrogens, C2H6. And then finally, for propane, we have 3 carbons, a total of 8 total hydrogens. Right? Right. And so we know that these are combustion reactions, right? Meaning that they mix with oxygen gas to create carbon dioxide and H2O water, right? So we can start off by putting O2 in all of these equations. So we have plus O2 plus O2 for propane, or for ethane, and also for propane. And then leads to the formation of CO2 and H2O. Right? And we have these products for all 3 reactions, right? For both methane, ethane, and propane. Right? For propane, CO2, and H2O. Right? Then, and from here, we can start putting in the nitrogen gas, right? Even though the nitrogen does not do anything within these equations, we need to represent it. We need to show that it is a part. So as you can see here, we'll add the mole fraction of 79/21 of the nitrogen gas. We'll be adding this to both sides of the equation. Right? Right. And we also do this for both ethane and propane, as they follow the same combustion process. Right? So 79/21 of nitrogen gas for both ethane and propane. And then, of course, it is also on the product side. Alright, alright. So now from here, we can start working on determining the stoichiometry for all these reactions. And we start off with methane. We have one carbon as well on both sides. However, we have four hydrogens in the methane as CH4. So we have two waters on the right hand side. We have two H2O, which causes us to have a total of four oxygens. And now multiplying this oxygen by 2. Then of course we have to represent this by multiplying the nitrogen also by the same coefficient. Right. And there we have it for methane. For ethane we have two carbons, so we change this carbon dioxide into two carbon dioxides. However, we have six hydrogens, so then we multiply three H2Os. Right? So we have a total of six hydrogens on both sides. Now for the total amount of oxygen, we have 4 in the carbon dioxide and 3 in the water. So we have a total of 7 oxygens. So we multiply this O2 by 7 halves. Right? 7 halves times 2 is just simply 7. And the same with the nitrogen on both sides of the equation. Right. Then finally for propane, we have 3 carbons on the left-hand side, so we have 3 carbon dioxides, causing us, and now we have 8 hydrogens, so we multiply the water by 4, so we have 4 H2Os, and for a total of 4 plus 6, a total of 10 oxygens, so we multiply this simply by 5. As well as with the nitrogens, again, we multiply those by the same coefficient. Okay, so now almost finished with the first part of determining the reaction stoichiometry. There's one major thing we're forgetting. It is in the beginning of the problem, it says that it burns with excess air, more specifically 20% of excess air. What this means is that there's 120% of air instead of what it is. There's a total of 20% more than what we need for the equation to take place. So what we want to do is we want to multiply the air on the left-hand side, which is these oxygen and nitrogen, by 100 or 120%, right? We want to do this for all three of the equations, right? So we're going to have all three of these be multiplied by 1.2. So we're going to erase this plus to add some space. Now, the whole air is multiplied by 1.2, which is adding 20%. Right. And this isn't all that we need to do, as increasing the left-hand side is going to cause something to happen with the product, something will happen to the right-hand side, right? And what is going to happen is it's going to add 0.2%, like we said, 20% of excess. And what we're going to do is for all three of these equations, we're going to be added 0.2 times how much oxygen is being utilized in the reactants. So we see that there's 2 O2, 2 oxygen gases, so we multiply by 2 O2, which now causes that to become 4, or 0.4 oxygen gas. We do this for both ethane and propane. So 0.2 multiplied by 7 halves of oxygen gas. And the same for propane, multiplied by 0.2 times 5 oxygen gases. However, this isn't all that happens to the right-hand side, as we need to make sure that the nitrogen is also multiplied by multiplied correctly. So what we're going to do is erase all of this out and multiply it by 1.2. However, since to make this easier, instead of 1.2, I'm going to be using a fraction. 6 over 5 is the same as 1.2, so I'm going to be multiplying that out. So for the methane, we're going to be multiplying 6/5 times 2, right? Times 2 and multiply that by the nitrogen gas. And then meanwhile for methane we have again 6/5, but now multiplied by 7/2, right? The same with ethane, we have 6/5 now multiplied by 5. And then we can all simplify all this out a little bit more. Let me do this. So we have 6/5 times 2, 6/5 times, or 7/2 times 5. Simplify that down. We now have 6/5 times 2, which is 12/5. Right? Then now for the 6/5 times 7/2, we have 42/10, but to simplify that, we'll do 21/5 is the most simple form. And then finally for ethane, or for propane, we had 6/5 times 5, which is simply equal to 6. And there we have it. Now have our three solved stoichiometries. So now looking on at part 2, it says that from starting from the energy balance equation, we want to derive the equation to determine the adiabatic flame temperature, along with being able to derive the expressions to calculate the ideal gas enthalpy for each species as a function of temperature, showing the ChemCat expression for Cp, and integrating this for the standard state temperature to the desired temperature T. So before we go ahead and do all of this, we want to remember that we're dealing with an adiabatic flame temperature, right? And this, the adiabatic flame temperature, we know that the gas laws gives us that the internal energy as well as the enthalpy is equal to 0 for this, as it remains constant. But what we want to do when we get started, so what we want to say is that the change in U, or the change in energy, is equal to the entropy at state 1 minus the one at state 2, right? And according to what we know that this change in energy is equal to 0, so that simply that the two states subtract, or the entropy of state 1 minus entropy of state 2 is equal to 0, which then causes H1 equal to H2, right? We know that the entropy of state 1 is equal to the entropy of state 2, right? And this H1 minus H2 right here, it can also be simply stated as the change in enthalpy, right? As the change in enthalpy is just change from 1 minus 1 to 2. And we also give an equation for the change in entropy, sorry, that we will be using for this problem. That is that the change in enthalpy divided by the change in time with constant pressure, right, multiplied by the change in temperature. And this denotes the total change in enthalpy. However, this little change in enthalpy minus change in time with constant pressure is also giving us something else, so that we know that this change in enthalpy can also be given as Cp, which is the specific heat capacity, the constant pressure for a given ethane or whatever it may be, times the change in temperature. Okay. And for large changes, there's a more specific equation that we use to find the more specific change in enthalpy, and which is integrals, right? So the integral of the enthalpy from state 1 to state 2 is simply equal to the integral of Cp, is the heat capacity with constant pressure, with respect to the change in temperature. Right. This is from temperature 1, or state 1, to state 2. So therefore, this could simply be written as the enthalpy of state 2 minus the enthalpy of state 1 is simply equal to that integral. The integral of state 1 to state 2 of the heat capacity with respect to, with the change in temperature. With respect to temperature, sorry. So then this can be written for H2 for the enthalpy of state 2 as H2 is equal to the integral of temperature 1, state 1, to temperature 2, state 2, of the heat capacity with respect to the temperature plus the enthalpy at state 1. Right? And there we have it. This is our equation that we'll be using now to be solving in Wolfram Alpha. Now for part 3, we are being asked to utilize ChemCAD to determine CP, the specific heat capacity for different materials, and here you can see equation 107 is what we'll be using to find CP. So you can see we are given A, B, C, D, and E, which are all constants specific to the specific material or specific compound that we're using. And so the heat capacity is equal to A plus B times the constant C divided by the temperature divided by the arc sine of C divided by temperature, all squared, plus D multiplied by the coefficient of E divided by the temperature, all over by cosine E divided by T, and all squared. So we go ahead and put these two different values into Wolfram Alpha to integrate and find the exact values. So for the first one, we're going to go to Wolfram Alpha and say that we want to integrate value. And for now, we'll be using B in here. We don't necessarily need to, as we're only looking for this, but just to make it more simple, we'll be using it. So we have B multiplied by we have C divided by the temperature, and we have that divided by the hyperbolic sine of C divided by temperature. Then we have all of this squared, right, power of 2. And then we have to use a comma T to explain that T is the variable what we're trying to integrate for. So we press enter, and we're given now the integral for that, which is B times C times the hyperbolic cotangent of C divided by temperature. Now we go ahead and do this for the second part, which is D multiplied by that whole thing. So again, from Wolfram Alpha, we integrate D multiplied by, we have E divided by T, and then that divided by the hyperbolic cosine of E divided by T. And then we have this whole thing to the squared to the power of 2. And then again, we want comma T, as that is what we are integrating for, or the variable that we're integrating. Now here we're given a value negative E times D times the hyperbolic tangent of E divided by temperature. So now that we've found the two different integrals and have a good equation for CP, we are now able to put it into our Python. So I've gone on ahead and put in the sort of the beginning of the Python code, and we've gone through this many times before. This GitHub is simply the website where we've given all this content and all the valuable information that we'll be using throughout this code. And as you can see, we were given all of these. We've achieved to reading all of these different values. And for example, if we were to open methane props, we see that gives us all this information for the molecular weight, critical temperature, the heat of formation, and all of that goes on. If we keep scrolling down, we see the liquid density, solid density, vapor pressure, heat of vaporization, and we finally go to the ideal gas heat capacity. In this ideal heat gas capacity, under you see that there's some coefficients, and we have 1, 2, 3, 4, and these coefficients are the values for A, B, C, D, and so on for our CP. And so we'll be using these values in order to create our code and so on. So let's get started. The first thing is first we want to create a variable that holds the properties of all the various compounds that we're going through, right? So we want to do a C sheet props. And then within it, we want to make it a list, right? We want to give all the different values that we're given. So if we recall back to our first part, we remembered that we were given methane first, as well as ethane and propane, right? And then from here, we came to the values of we also had nitrogen in our left hand side, right? So nitrogen, and then for the right hand side, we have carbon dioxide, all one word. We recall we also had oxygen and water, so put water back here, and oxygen was actually on the left hand side, so we're going to put it back here. Alright, there we have it. Press shift enter and we have all these values. And there's an issue because with the propane has there many different types, so we want to specifically make it in propane. So now what we want to do is we want to create a function that will then return us values for each of those properties, right? So what we want to do is define a function, and what we want to do is find CP, right? So I'm going to call this function integrate CP, right? That's a function of t. And then what we're going to want to return is the values that we received from alpha. And we want to put these values and the integrals into our return function. So like we were talking about earlier, as you can see in here, we can pull it back up. Ethane props, pull that up. Again, we go back down and see what we're solving for, as we want to see the ideal gas heat capacity. Again, we're given A, B, C, D, E, F, and G values, right? We'll be using this ideal gas to determine CP. So in the equation for return, we'll have return CP dot, we have IGA, we have P dot IG, and then we'll be using A, then multiply that by T, right? Then we'll be putting this in, so then we have B times C, right? So plus P dot CP, and then we'll be using B this time, times P dot CP C, And then we have um, we'll use times NP with cotangent, so cotangent H of, we have C divided by T, so C divided by temperature, right? And actually this there should be a divided sign instead of a multiplication. And then if we go see our second integral, we're given negative ED this, so we're going to be using a negative sign, right? We're subtracting, and then we have P dot CP by G, and then we'll be using E times P dot CP, and we'll be using E now, right? And then we'll be using the hyperbolic tangent, so divided by NP dot tangent H of, and then we have E divided by T, the temperature, so we have P dot CP E divided by temperature. And there we have it. This being a multiplication, actually. So now that we've create this function, we also want to create a new function, right? And this function we'll be using is the one that we created down here, right? Find the enthalpy of the second state, right? So what we're going to do is create a function and call it h for the enthalpy, right? H of t. And we're going to have it return those values. So we want to return the heat of formation of ideal gas. So we have P dot heat of formation of an ideal gas, and plus integrate this value of T, right? So integrate Cp, the value of T. Then we want to subtract from it the given value in our homework, right? Put integrate Cp. And then if you go back, we see that we're given a value of standard state temperature, which is 298.15 degrees Kelvin. If you put that in, 298.15, let's hit Shift Enter. Right. So now we check this out, see if it's all good. So if we put the enthalpy, say, of 300 degrees Kelvin, see what happens. All right, we're given a list. We're given 1, 2, 3, 4, 5, 6, 7 values, which are for the methane, ethane, propane, oxygen, nitrogen, carbon dioxide, and water values, right? So that when the temperature is equal to 300 degrees, that the methane goes through an enthalpy of negative 8,800 joule per Kelvin, right? And one problem though is these numbers are a bit too big, as you can notice. So what we need to do is we need to divide all this by 1,000 to make sure that the units work out correctly. Or sorry, bad math. All of this divided by 1,000. We run it again, and now we're given that for methane we have negative 7.5, negative 8.4 for ethane, and so on. So now we have reached part 4, where we have to code our model and solve for the temperature for this adiabatic flame. Right? So if we go back looking at our Python code so far, from now what we need to do is we need to start creating arrays and matrices to find the temperature. And so we start off by creating an array with the different moles or amount of moles that we have, right? So I'm just going to call this array fuel, and it's going to be an array, numpy more specifically. And we're going to be using the values that we're given. So we have 95 methane, 4 ethane, and 1 propane. So we're going to act like there's a total of 1. So we're going to have 0.94 ethane or methane, 0.04 of methane, and 0.01 of propane. Right. Then we're also going to want to create an array for the amount of carbons and hydrogens within each of these. So I'm going to do it. I'm actually going to call this N fuel and then call this NC for this new. I'm going to do an array, and it's going to have um, two columns and 3 rows, right? So, or 3 columns and 2 rows. So we're going to have 2 columns. So for the first one, there's 1 carbon, and there is for 4 hydrogens, right? And for methane, we have 2 carbons and 6 hydrogens. Then for the final propane, we have 3 carbons for 8 hydrogens, right? Shift enter. And for here, it's something you can extra bracket to say that these are 3 different values, 3 different arrays. Should be all good, right? Then, so from here, we create a matrix multiplication to find the values or the amount of moles of carbon and the amount of moles of hydrogen. So what we do is NC comma H is equal to, and what we do is going to multiply these two. So N fuel divided by NCH. Then we continue with what else we know. Well, we know for carbon dioxide, the amount of carbon dioxide is equal to the amount of carbons, right? And for the moles of H2O is equal to the amount of moles of hydrogen divided by 2, right? And then finally, the amount of oxygen gas is equal to, we have NH2O divided by 2 plus the amount of moles of carbon dioxide. Right. And finally, the amount of moles of nitrogen gas, right, is simply what we had, so 79/21 of NO2, right? There we have it. So now we have all the amount of moles. Software, we want to create 2 different functions for the amount of moles going in and the amount of moles going in, the amount of moles going out. Right. So for our n in, what we're going to want to do is we're going to add something towards the end of n fuel. So to do that, we use numpy concatenate. So numpy.concatenate. And then to use this, so we'll be putting it in within n fuel, right? What we're going to be putting in is the values of what's going in. So as we can see, we have the values of O2, right, oxygen gas, along with nitrogen, right? And then we want to make sure that this is going as an array, right? So np.array of that, right? Then we also want to make sure we add the amount of CO2 and H2O that's going in as well, which in this case is 0, right? We have nothing going in. And that's it, right? Now, on the other hand, we gotta find what's coming out, right? And we're gonna create an array for what's coming out, so that we have total values. So as we look up, we have for methane, ethane, and propane, we have 0 going in for all of those, right? And as well for oxygen, that's coming out. Then we're just gonna simply want the amount of moles of nitrogen gas with amount of moles of CO2, and finally amount of moles of H2O. There we go. We have what we have coming in, amount of moles coming in, and amount of moles coming out now. Now that we've gotten that, the main idea we want to create a function based off of what we worked on in problem 2 or in part 2, right? We want to make sure that the entropy going in is equal to that is going out, right? So we're going to define a function and call it equations, and we're going to have a vector inside of it, right? And then, but this vector we're just going to it's simply going to be t, so t equals vector. Okay. More specifically, this vector is the first vector for number 1. First in this vector is going to be t1, right? And so for a return, what we're going to want is a dot product, right? So what we're going to do is mp dot dot, and then within it we're going to multiply, we're going to have enthalpy T respect with n in, we're going to subtract the other, and mp dot, we have H with the original temperature value, which is 298 Kelvin, right? With n out, right? And there we have it. We have our function with our return values. Or actually should have this being the amount of moles coming out and this being the amount of moles coming in, right? So now that we have our equations, we are now able to use it to find our temperature, right? And we go back, we call root function to be solving this, right? And we're going to be using equations, right? And we'll be using a guess, and let's guess of 1,000 for now, right? Shift enter, and we get these values, right? And we only want the final, so we do dot x. We're given the array with the value. If we simply call it upon 0, it just gives us the value. This value is 2,332 degrees Kelvin, which is the total temperature of what the flame, the temperature of the flame coming out at that time. So then there's one thing we were missing, right? As we can remember, if we go back, we see that it is burnt with 20% of excess air, right? And we didn't put that anywhere in the code. So the idea now is seeing how the excess air affects the final temperature and this process as a whole. So to change that out, I'm just going to call up here and create a new variable. I'm going to call it excess in air, right? And it's simply going to be 0.2, right? Because it's 0.2 more. And the only thing that it really affects, looking back at our equations, is the amount of oxygen. So this whole thingamajigger, amount of moles, is going to be multiplied by 1 plus the excess air, which causes it to become 1.2, right? Then now the only other thing that we changed, the amount of moles going in would not change, but on the other hand, the amount of moles out is going to change, as the O2, the amount of moles O2, will be different. It is no longer 0, but is now dependent on excess air, right? So what I'm going to do is make this N of O2 multiplied by excess air, right? There we have it. So now we click Shift Enter and we see what difference this caused. So we're currently at 2,332 degrees Kelvin without excess air, and with added excess air we come to a temperature of 2,063 degrees Kelvin. So there we have it. Hopefully this video was some usage to you and helped you in some different ways. Thank you for watching and have a great day.